Hello, good morning, class. This is Dr. Gu again. This is going to be our last lecture of this semester. Discuss about some updates on rubber elasticity theory. So, in the last chapter, our focus is on how to design a different theory to capture what is rubber elasticity. So, what we did in the last few lectures is talk about fundamentals of mechanics, discussed how chain conformation can be linked to entropy and how we can use loss of entropy to translate to rubber elasticity force. Okay, we were able to discuss the lecture and understand how we can predict the stress as well as modulus based on number of entanglements or entanglements between molecular weights. So this is where we were left, and this is a part of the important lecture where we discussed what is a G in terms of modulus depends on crosslink molecular weight mx, or you can understand this is a number of crosslink points within a given volume. So in other words, we know the theory nicely describes if the temperature increases or crosslink density increases, your modulus or your strength of the rubber is getting stronger. Okay. So what we're going to do in today's lecture. So today's lecture is slightly different with what we talked about before. I want to go back to a slide where we talked about a few assumptions for rubber elasticity theory. Let me see. We discussed that this is going to be a finite network, and initial network is isotropic and volume constant during deformation. So this first one is true at a low degree of strain. So if you imagine, if you stretch a chain at the initial stage, it will be Gaussian coil, but if you stretch the rubber a lot and assume it's 4 or 5 times difference with what your initial length, then your coil is no longer a Gaussian coil, and it's a very much elongated coil, and your value will be different and depends on degree of strain. So the first assumption does not hold very well in high degree of strain for rubber material, and we will see why that's the case, and we will discuss what the results look like in today's lecture. In the second part is where we discuss where the initial network is isotropic. So this is usually hold true, and in many cases where your rubber gonna start with isotropic state. The volume remain constant, and that's pretty much the case. But again, there is always gonna be a deviation from ideal Poisson ratio of 0.5 or ideal elastomer. So based on the theory we had, people were able to do an example test where you get a rubber, you plot tensile or compression force with respect to compression or extension, and you were able to see how does the mechanical response of the material, and you can tell the theoretical curve is showing the solid line, while the dashed line linked by between the dots are the way people discuss about those material, and you can tell it is pretty much a good agreement between your theory and your data. But if you watch carefully in the compression region, it is very good. However, in the tensile region or extension region, your data start to deviate more and more with a higher degree of strain. So look at here, when your strain is 2.0, it is much bigger difference. This is especially true when you stretch a rubber at very high strain. So look at here where you have extension ratio. It's basically draw ratio from 1 to 8. And the higher the extension ratio, 8 means we deform the rubber 8 times of original length. So 8 is very high value in terms of deformability. And you can see the theory is what we discussed, our entropy theory predicted that your behavior will behave like this, but in reality, if you can tell, I would call maybe between 1 to 5 degree of strain. It's pretty much similar, and there is some deviation, but not terribly bad. But once your strain is above 5, your rubber elasticity deviates dramatically with what the theory, and this is what you see. It can be up to 100% differences between theory predict the force per unit area will be about 3.0, while the reality people measured is already exceeding 6. That's a big difference. We discussed this is pretty much due to the Gaussian coil assumption. Gaussian coil assumption is not right. It's not valid when REE is close to LC, right? The second is a strain-induced crystallization can be happen. So the first one is easy to understand. So the second one is what happens when you have a rubber material. A lot of time the rubber shows very unique properties because it has strain-induced crystallization. So what this term means is when you stretch a rubber, in a normal case crystallization happens when you change the temperature. If you heat and cool, when you cool the material down to its crystallization temperature, your material starts to crystallize, and you see you would start to see changes in the degree of crystallinity. But additionally, the strain can also induce crystallization. So if you stretch a polymer, if it's above a certain threshold, it will start to crystallize, and this is what people call it strain-induced crystallization. Okay. Those crystallization happens to act as a physical crosslink. And it's not a covalent crosslink, but it's something similar. It's called a physical crosslink, where the crystallized points basically act as a crystalline points. And as you can see, if we happen to have physical crosslink points between those covalent crosslink points, then you would have artificially increased crystalline density. And this would result in an increase of the modulus of your material. As this is partially the reason of why this has the rapid increase, a lot of crystallization happens here. Meantime, there is a lot of deviation from Gaussian theory, so this is something you should keep in mind when you use this theory. Now the question is, how do we address this? How do we solve this problem? Don't make it happen. And there's a couple researchers developed several theories, so we're going to talk about a couple development after the Flory-Huggins and others developed the entropic rubber elasticity theory. So a couple assumptions, and there is no changes in the internal energy at constant temperature P and U, and there's no change in volume at T and P. And this is one of the reasons we can link the delta, the forced to partial derivative of the delta G to displacement L. And this has been discussed quite nicely, right? So Gaussian core deformation distribution, we talked about it, and it's likely need a fix up because it's not going to work out. Chain conformation before the deformation is the same as chain conformation on cross-linked states. So this gonna be related to another theory, how we can address what the conformation change before and after. This is also important because if the crosslink influence the morphology, then it will impact our theory. But most of the time, it's not a big effect, not as big as the assumption 3. Okay. And junction point affine to the macroscopic deformation. So as we talked about, when we stretch a rubber material, your crosslink point will deform agreed with macroscopically. This is not always true. Deformation is sometimes inhomogeneous in the local scale. So some point might deform slightly bigger than the other. So this causes modification needed to understand how to address this affine deformation. Last is a number of elasticity effective strain per unit volume is given by this. This is pretty much easy to fix, and this is all we need to do is to get a real effective strain. Okay, not just apparent effective. You can back calculate based on modulus to what is effective value. So first is let's see what the assumption we can do. Chain conformation for the strain follows Gaussian distribution. As I mentioned, this is one of the big reasons we need to address this, and this was done by adding an inverse Langevin function. This is done by Jung. So this approach is slightly different, where people added additional terms to count for non-Gaussian behavior. Okay, so if you look at the force inverse relationship, if you plot 1 divided by x, and you will see if this is the value, then inverse relationship will show this particular shape of the response, and that will ideally match this part. But if you only keep this piece, then your low deformation region cannot be captured. So a smart way is to combine the conventional approach where we had, and as well as add into additional term to this inverse Langevin function to capture those non-ideal Gaussian coil deformation. Okay, so this is basically what people showed in the probability of the distribution of chain and function P, dependence of nx and h. The other one is regarding the idealized chain network. This assumption says before deformation is the same as after deformation. And this one is just a need to introduce a conceptual frontal factor, because crosslink might slightly change the chain conformation. So what people did is to slightly modify what is h value. So added hi and h0. And these two factors, hi is after crosslink, h0 is before the crosslink. So this accounts in slightly difference in the end-to-end distance change. As you can see, this does not affect the overall shape, but it will modify what is initially the shape of the original stress strain curve. Okay. And the other one is a affine deformation. Affine deformation discusses how your polymer will deform affinely to the macroscopically. This is to introduce an idea of phantom network to lower the effective number of crosslink. Phantom network, what does phantom means? Phantom means something is not real, something is idealized. Like Phantom of the Opera is something not ghost-like. Okay, so this ghost-like network is basically the people address the way how you can attribute to the affine network limitation. Ghost network means we put a black close to what the network is. We don't care, or we don't want to understand in every single detail where the network crosslink point is, but we instead introduce this ghost term, and this ghost term has a unique ability to say that you have a network crosslink point. This crosslink point is somewhere in that area, and it will stay there. And using this ghost network, it will allow you to capture the deformation should be affine to macroscopically. Okay, so this is again a minor modification to address this prefactor term. And VE and VX, V is crosslink density. Vx is a consideration of after we crosslinked, okay, or after we modify this Fenton network. What is Fenton network's influence or correction factor? So VE minus Vx will be the real crosslink density, while the VE was originally the crosslink density without accounting the Fenton network effect. So this network will basically, there's also people start a term call it a network. They can imagine also would behave like a chain would fluctuate around its ideal mean position. So it's in other words, let me get my pen. In other words, Fenton network basically says you are no longer fixed here. This crosslink point could fluctuate within this sphere, and within this sphere allow you to slightly modify the crosslink density. So that's a difference between the two. There's one more modification we need to do is effective of strain per unit network is given by this rho multiplied by Avogadro constant divided by mx. Mx is a crosslink, a molecular weight between the crosslink points. So there is also need to consider there's defect in the crosslink, and there's trapped entanglement between the polymer chain. So what this means is if you have crosslink points, they only passes two p's and they are not cross-linked again into the network. So it's like a dangling loops, and this need to be considered as a way to modify it by using another parameter called ME. ME is where we consider this modified entanglement density in addition to mx. So this is what the original term. This is the additional piece of fitting parameter. So this fitting parameter will allow one to capture better cross-link density within the network. Okay. So combining everything together, a most popular rubber elasticity theory modification is called munirivling equation. So what this does is where people add, this is original term where we get stress is dependence on a constant of prefactor and lambda minus 1 divided by lambda square. And what Muni based on the continuum argument is we can add a second continuum term C2, and its dependence on the extension ratio is weaker, so it's no longer dependent on lambda but dependent on 1 divided by lambda and 3. So okay, and by combining these two we can see we can now modify the original equation to have C1 and C2 term, and C1 and C2 are two constant, and you can get the C1 C2 based on measurements. So how do we get the C1 and C2? C1 and C2 are two constant, and the way we get it is basically based upon measurement of stress and strain. So we can measure the stress, we can measure the strain, but now instead of plot with stress versus strain, we need to modify the stress with stress divided by lambda minus 1 divided by lambda square. So this is a new y value, and you can plot against this 1 divided by lambda. This would be x. So again, I'm gonna ask you to take a look at this equation. Y equals a plus bx. So here y is basically plotted as stress divided by the strain lambda minus 1 divided by lambda square, and stress x is equals to 1 divided by lambda. So if you plot this way, the intercept with y-axis will give you what is a value or C1, and the slope of this curve will give you C2. Something like our osmotic pressure and the measurement of the secondary coefficient and molecular weight, but instead here it's giving you what is C1, C2. So you can extract the C1, C2 value, and this is a good empirical approach and give you a much better fitting into the experimental data in the rubber elasticity theory. Okay. With that, I think there will be end of the lecture. So the last part of today's lecture is really just some fix up about rubber elasticity theory, tell you some of the limitation and what people has considered to address the problem. It's still a very fascinating problem to polymer physicists. You can, if you go to an American Physical Society conference, you can still see rubber elasticity theory still have quite a lot of research group to work on and developing your rubber materials. With that, I'm gonna wrap up today's lecture. It's the end of the lecture, so I thank everybody for your attention throughout the class. And this Thursday, I'm gonna resume the class to answer the homeworks for the rubber elasticity theory part. And with that, I will end today's class. And I will also have time to answer any questions related to the final exam as well as the other tests. So I'll see everybody this Thursday, and bye for now.